Welcome to the I Can't Sleep podcast, where I help you drift off one fact at a time. I'm your host, Benjamin Boster, and today's episode is about Cern. Thanks to Julie Gibson for sponsoring today's episode. If you'd like to sponsor an episode, check out my website and go to the Request a Topic section to fill out the details there. The European Organization for Nuclear Research, known as Cern, is an intergovernmental organization that operates the largest particle physics laboratory in the world. Established in 1954, it is based in Cern, western suburb of Geneva, on the France-Switzerland border. It comprises 24 member states. Israel, admitted in 2013, is the only full member geographically out of Europe. Cern is an official United Nations General Assembly observer. The acronym Cern is also used to refer to the laboratory. In 2023, it had 2,666 scientific, technical, and administrative staff members, and hosted about 12,370 users from institutions in more than 80 countries. In 2016, Cern generated 49 petabytes of data. Cern's main function is to provide the particle accelerators and other infrastructure needed for high-energy physics research. Consequently, numerous experiments have been constructed at Cern through international collaborations. Cern is the site of the Large Hadron Collider, LHC, the world's largest and highest energy particle collider. The main site at Cern hosts a large computing facility, which is primarily used to store and analyze data from experiments as well as simulate events. As researchers require remote access to these facilities, the lab has historically been a major wide-area network hub. Cern is also the birthplace of the World Wide Web. The convention establishing Cern was ratified on September 29, 1954, by 12 countries in Western Europe. The acronym Cern originally represented the French words for Conseil européen pour la recherche nucléaire, European Council for Nuclear Research, which was a provisional council for building the laboratory, established by 12 European governments in 1952. During these early years, the council worked at the University of Copenhagen under the direction of Niels Bohr, before moving to its present site near Geneva. The acronym was retained for the new laboratory after the Provisional Council was dissolved, even though the name changed to the current Organisation Européenne pour la Recherche Nucléaire, European Organization for Nuclear Research, in 1954. According to Lou Kowarski, a former director of Cern, when the name was changed, the abbreviation could have been the awkward OERN, and Werner Heisenberg said that this could still be Cern even if the name is not. Cern's first president was Sir Benjamin Lochspicer. Eduardo Amaldi was the general secretary of Cern at its early stages, when operations were still provisional. And the first director general, 1954, was Felix Bloch. The laboratory was originally devoted to the study of atomic nuclei, but was soon applied to the higher energy physics concerned mainly with the study of interactions between subatomic particles. Therefore, the laboratory operated by Cern is commonly referred to as the European Laboratory for Particle Physics, which better describes the research being performed there. In the sixth session of the Cern Council in Paris from June 29th to July 1st, 1953, the convention establishing the organization was signed, subject to ratification by 12 states. The convention was gradually ratified by the 12 founding member states: Belgium, Denmark, France, the Federal Republic of Germany, Greece, Italy, the Netherlands, Norway, Sweden, Switzerland, the United Kingdom, and Yugoslavia. Several important achievements in particle physics have been made through experiments at Cern. They include 1973, the discovery of neutral currents in the Gargamel bubble chamber. 1983, the discovery of W and Z bosons in the UA1 and UA2 experiments. 1989, the determination of the number of light neutrino families at the Large Electron-Positron Collider LEP, operating on the Z boson peak. 1995, the first creation of anti-hydrogen atoms in the PS210 experiment. 1995 to 2005, precision measurement of the Z line shape, based predominantly on LEP data collected on the Z resonance from 1990 to 1995. 1999, the discovery of direct CP violation in the NA48 experiment. 2000, the heavy ion program discovered a new state of matter, quark-gluon plasma. 2010, the isolation of 38 atoms of antihydrogen. 2011, maintaining antihydrogen for over 15 minutes. 2012, the discovery of a boson with mass around 125 gigaelectronvolts per c squared, consistent with the long-sought Higgs boson. In September 2011, Cern attracted media attention when the Opera collaboration reported the detection of possibly faster-than-light neutrinos. Further tests showed that the results were flawed due to an incorrectly connected GPS synchronization cable. In 1984, Nobel Prize for Physics was awarded to Carlo Rubbia and Simon van der Meer for the developments that resulted in the discoveries of the W and Z bosons. The 1992 Nobel Prize for Physics was awarded to Cern staff researcher Georges Chapac for his invention and development of particle detectors, in particular, the multi-wire proportional chamber. The 2013 Nobel Prize for Physics was awarded to François Englert and Peter Higgs for the theoretical description of the Higgs mechanism in the year after the Higgs boson was found by Cern experiments. The next computer used by British scientist Sir Tim Berners-Lee at Cern became the first web server. This Cisco Systems router at Cern was one of the first IP routers deployed in Europe. A plaque at Cern commemorates the invention of the World Wide Web by Tim Berners-Lee and Robert Cailliau. Cern pioneered the introduction of TCP/IP for its Internet, beginning in 1984. This played an influential role in the adoption of the TCP/IP in Europe. In 1989, the World Wide Web was invented at Cern by Tim Berners-Lee. Based on the concept of hypertext, the idea was designed to facilitate information sharing between researchers. This stemmed from Berners-Lee's earlier work at Cern on a database named Enquire. A colleague, Robert Cailliau, became involved in 1990. In 1995, Berners-Lee and Cailliau were jointly honored by the Association for Computing Machinery for their contributions to the development of the World Wide Web. A copy of the first web page created by Berners-Lee is still published on the World Wide Web Consortium's website as a historical document. The first website was activated in 1991. On April 30th, 1993, Cern announced that the World Wide Web would be free to anyone. It became the dominant way through which most users interact with the Internet. More recently, Cern has become a facility for the development of grid computing, hosting projects including the Enabling Grids for eScience, e.g., and LHC Computing Grid. It also hosts the Cern Internet Exchange Point, CIXP, one of the two main Internet exchange points in Switzerland. As of 2022, Cern employs 10 times more engineers and technicians than research physicists. Cern operates a network of 7 accelerators and 2 decelerators, and some additional small accelerators. Each machine in the chain increases the energy of particle beams before delivering them to experiments or to the next more powerful accelerator. The decelerators naturally decrease the energy of particle beams before delivering them to experiments or further decelerators. Before an experiment is able to use the network of accelerators, it must be approved by the various scientific committees of Cern. Currently, as of 2022, active machines are the LHC accelerator and the LINAC-3 linear accelerator, generating low-energy particles. It provides heavy ions at 4.2 mega-electron volts per Dalton for injection into the low-energy ion ring, LIR. The low-energy ion ring, LIR, accelerates the ions from the ion linear accelerator LINAC-3 before transferring them to the proton synchrotron, PS. This accelerator was commissioned in 2005 after having been reconfigured from the previous low-energy antiproton ring, LEAR, LEAR. The LINAC-4 linear accelerator accelerates negative hydrogen ions to an energy of 160 electron volts. The ions are then injected to the proton synchrotron booster, PSB, where both electrons are then stripped from each of the hydrogen ions, and thus only the nucleus containing one proton remains. The protons are then used in experiments or accelerated further in other Cern accelerators. LINAC-4 serves as the source of all proton beams for Cern experiments. The proton synchrotron booster increases the energy of particles generated by the proton linear accelerator before they are transferred to the other accelerators. The 28 giga-electron proton synchrotron, PS, built during 1954 to 1959 and still operating as a feeder to the more powerful SPS and to many of Cern's experiments. The superproton synchrotron, SPS, a circular accelerator with a diameter of 2 kilometers built in a tunnel, which started operation in 1976. It was designed to deliver an energy of 300 giga-electron volts and was gradually upgraded to 450 giga-electron volts. As well as having its own beam lines for fixed target experiments, currently COMPASS and NA62, it has been operated as a proton-antiproton collider, the SPPS collider, and for accelerating high-energy electrons and positrons, which were injected into the Large Electron-Positron Collider, LEP. Since 2008, it has been used to inject protons and heavy ions into the Large Hadron Collider, LHC. The Online Isotope Mass Separator, ISOLDE, which is used to study unstable nuclei. The radioactive ions are produced by the impact of protons at an energy of 1.0 to 1.4 giga-electronvolts from the proton synchrotron booster. It was first commissioned in 1967 and was rebuilt with major upgrades in 1974 and 1992. The antiproton decelerator, AD, which reduces the velocity of antiprotons to about 10% of the speed of light for research of antimatter. The AD machine was reconfigured from the previous antiproton collector, AC machine. The extra-low energy antiproton ring, ELENA, which takes antiprotons from AD and decelerates them into low energies, speeds, for use in antimatter experiments. The AWAKE experiment, which is a proof of principle plasma wake field accelerator. The Cern Linear Electron Accelerator for Research, CLEAR Accelerator Research and Development Facility. Many activities at Cern currently involve operating the Large Hadron Collider, LHC, and the experiments for it. The LHC represents a large-scale, worldwide scientific cooperation project. The LHC tunnel is located 100 meters underground, in the region between Geneva International Airport and the nearby Jura Mountains. The majority of its length is on the French side of the border. It uses the 27-kilometer circumference circular tunnel previously occupied by the Large Electron-Positron Collider, LEP, which was shut down in November 2000. CERN's existing PS/SPS accelerator complexes are used to pre-accelerate protons and lead ions, which are then injected into the LHC. 8 experiments, CMS, Atlas, LHCb, Modal, Totem, LHCF, Phaser, and Alice, are located along the collider. Each of them studies particle collisions from a different aspect and with different technologies. Construction for these experiments required an extraordinary engineering effort. For example, a special crane was rented from Belgium to lower pieces of the CMS detector into its cavern, since each piece weighed nearly 2,000 tons. The first of the approximately 5,000 magnets necessary for construction was lowered down a special shaft in March 2005. The LHC has begun to generate vast quantities of data, which CERN streams to laboratories around the world for distributed processing, making use of a specialized grid infrastructure, the LHC computing grid. In April 2005, a trial successfully streamed 600 megabits per second to 7 different sites across the world. In August 2008, the initial particle beams were injected into the LHC. The first beam was circulated through the entire LHC on the 10th of September 2008, but the system failed 10 days later because of a faulty magnet connection, and it was stopped for repairs on September 19, 2008. The LHC resumed operation on November 20, 2009, by successfully circulating 2 beams, each with an energy of 3.5 tera-electron volts. The challenge for the engineers was then to line up the 2 beams so that they smashed into each other, This is like firing two needles across the Atlantic and getting them to hit each other, according to Steve Myers, Director for Accelerators and Technology. On March 30th, 2010, the LHC successfully collided two proton beams with 3.5 tera-electron volts of energy per proton, resulting in a 7 tera-electron volt collision energy. This was enough to start the main research program, including the search for the Higgs boson. When the 7 tera-electron volt experiment period ended, the LHC increased to 8 tera-electron volts, 4 tera-electron volts per proton, starting March 2012, and soon began particle collisions at that energy. In July 2012, Cern scientists announced the discovery of a new subatomic particle that was later confirmed to be the Higgs boson. In March 2013, Cern announced that the measurements performed on the newly found particle allowed it to conclude that it was a Higgs boson. In early 2013, the LHC was deactivated for a 2-year maintenance period to strengthen the electrical connections between magnets inside the accelerator and for other upgrades. On April 5, 2015, after 2 years of maintenance and consolidation, the LHC restarted for a second run. The first ramp to record-breaking energy of 6.5 tera-electron volts was performed on April 10, 2015. In 2016, the design collision rate was exceeded for the first time. A second 2-year period of shutdown began at the end of 2018. As of October 2019, the construction is ongoing to upgrade the LHC's luminosity in a project called High Luminosity LHC. This project should see the LHC accelerated upgraded by 2026 to an order of magnitude higher luminosity. As part of the HL-LHC upgrade project, also other Cern accelerators and their subsystems are receiving upgrades. Among other work, the LINAC-2 linear accelerator injector was decommissioned and replaced by a new injector accelerator, the LINAC-4. Decommissioned accelerators. The original linear accelerator, LINAC-1, operated 1959 to 1992. The LINAC-2 linear accelerator injector accelerated protons to 50 mega-electron volts for injection into the proton synchrotron booster, PSB. Operated 1978 to 2018. The 600 mega-electron volt synchrocyclotron, SC, which started operation in 1957 and was shut down in 1991, was made into a public exhibition in 2012 to 2013. The intersecting storage rings, ISR, an early collider built from 1966 to 1971 and operated until 1984. The super proton antiproton synchrotron, SPPS, operated 1981 to 1991. A modification of super proton synchrotron to operate as a proton-antiproton collider. The Large Electron Positron Collider, which operated 1989 to 2000 and was the largest machine of its kind, housed in a 27-kilometer-long circular tunnel, which now houses the Large Hadron Collider. The LEP pre-injector accelerator complex, consisting of 2 accelerators, a linear accelerator called LEP injector LINAC, and a circular accelerator called electron-positron accumulator. The purpose of these accelerators was to inject positron and electron beams into the Cern accelerator complex, more precisely to the proton synchrotron, to be delivered to LEP after many stages of acceleration. Operational 1987 to 2001. After the shutdown of LEP and the completion of experiments that were directly fed by the LPI facility was adapted to be used for the CLIC Test Facility 3. The low-energy anti-proton ring was commissioned in 1982. Lear assembled the first pieces of true antimatter in 1995, consisting of 9 atoms of antihydrogen. It was closed in 1986 and superseded by the anti-proton decelerator. The Lear apparatus itself was reconfigured into the low-energy ion ring, ion booster. The anti-proton accumulator, built 1979 to 1980, operations ended in 1997, and the machine was dismantled. Stored antiprotons produced by the proton synchrotron for use in other experiments and accelerators, for example the ISR, SPPS, and Lear. The latter half of its working life operated in tandem with antiproton collector to form the antiproton accumulation complex. The antiproton collector, built 1986 to 1987, operations ended in 1997, and the machine was converted into the antiproton decelerator, which is a successor machine for low-energy antiproton ring. Operated in tandem with the antiproton accumulator, and the pair formed the antiproton accumulation complex, whose purpose was to store antiprotons produced by the proton synchrotron for use in other experiments and accelerators, like the low-energy antiproton ring and superproton antiproton synchrotron. The Compact Linear Collider Test Facility 3, which studied feasibility for the future normal conducting linear collider project. In operation 2001 to 2016. One of its beam lines has been converted from 2017 on into the new Cern Linear Electron Accelerator for Research facility. Cern, in collaboration with groups worldwide, is investigating 2 main concepts for future accelerators: a linear electron-positron collider with a new acceleration concept to increase the energy, and a larger version of the LHC, a project currently named Future Circular Collider. The smaller accelerators are on the main Meran site, also known as the West Area, which was originally built in Switzerland alongside the French border, but has been extended to span the border since 1965. The French side is under Swiss jurisdiction, and there's no obvious border within the site, apart from a line of marker stones. The SPS and LEP and LHC tunnels are almost entirely outside the main site, and are mostly buried under French farmland and invisible from the surface. They have surface sites at points around them, either as the location of buildings associated with experiments or other facilities needed to operate the colliders, such as cryogenic plants and access shafts. The experiments are located at the same underground level as the tunnels at these sites. 3 of these experimental sites are in France, with Atlas in Switzerland, and some of the ancillary cryogenic and access sites are in Switzerland. The largest of the experimental sites is the Prévesson site, also known as the North Area, which is the target station for non-collider experiments on the SPS accelerator. Other sites are the ones which were used for the UA1, UA2, and the LEP experiments. The latter are used by LHC experiments. Outside the LEP and LHC experiments, most are officially named and numbered after the site where they were located. For example, NA32 was an experiment looking at the production of so-called charmed particles and located at the Prevesson North Area site. WA22 used the Big European Bubble Chamber, BEBC, at the Meran West Area site to examine neutrino interactions. The UA1 and UA2 experiments were considered to be in the underground area, i.e., situated underground at sites on the SPS accelerator. Most of the roads on the Cern, Meran, and Prevesson sites are named after famous physicists, such as Wolfgang Pauli, who pushed for Cern's creation. Other notable names are Richard Feynman, Albert Einstein, and Bohr.